welcome back to MFP 510. In this lecture, I want to show you how to solve a maximization problem using the graphical method. And I also want to say that, this is in your textbook, and I strongly encourage you to read this. I personally think it is absolutely invaluable. So I'm going to use the following example. So let's say, better do this. I have the following function. I'm going to keep it simple. 5x1 plus 10x2, subject to the following constraints. Subject to, so x1 has to be less than or equal to 12. x2 less than or equal to 8. And then x1 plus x2 has to be less than or equal to 14. And then, of course, I have my non-negativity constraints, x1, x2 greater than or equal to 0. Okay. So first thing we're going to do is I'm going to show you this, try to show this graphically. So I think what I'm going to do, kind of put my graph here, and then I'm going to kind of leave some room down here to work out some of these formulas. Well, all right, so the first thing is, actually, what I should say is, look, x1, x2 greater than or equal to 0, that confines us to this quadrant of our Cartesian plane, right? So again, here is x1, and here, of course, is x2. And again, notice we have to have 0 or positive quantities of x2, 0 or positive quantities of x1, right? Okay, so notice here, x1 has to be strictly, 12 or less. Well, notice what I like this problem. The reason I wanted to show this to you is, again, it reiterates this notion that x2 does not have to be in every constraint, right? In this first constraint, I just have x1. In this constraint, I just have x2. So in other words, in this constraint, you can think of this as x1 plus 0 x2 less than or equal to 12. Here you could think of this one as 0x1 plus 5x2. So the point that I'm trying to get at is, again, not all of your x's have to be in every constraint. All right, so let me get rid of this. Okay, so let's start drawing this out. This first one is pretty simple, right? x1 has to be less than or equal to 12. So what I'm going to do, I'm just going to draw a line. Here's 12. And less than or equal, what I'm going to do, I'm going to do this. So less than or equal, right, that's that area. Okay? Okay, x2 less than or equal to 8. All right. So here's 8, right? Less than or equal to, I'll use green, right? That's this area, right? Okay, so what have we essentially established? Well, look, just based on these first two constraints, right, our objective function is going to be maximized somewhere in this area, right? Because it's only in this, at least right now, it's only in this area that we are satisfying the first constraint and the second constraint, right? Now, I know I need this third constraint, but the point is, at least right now, we know we're going to be somewhere in here. So, oh, brothers, that certainly did not go as planned. Okay, so let me just see if I can do this. Oh boy, okay, never mind. Okay. Well, yes, I can't erase part of the line. So we're going to have to leave all this extra stuff laying around. Okay. So now what I need to do is draw in this third constraint, right? So what I always recommend to my students is say, look, right, x2 is on, we always put x2 on the vertical axis, right? So if you think about, your equations, you always wanted x2 to equal something, right? Whatever is on the vertical axis, that always goes on the left-hand side of your equation, right? So the point I'm trying to get at is solve these equations. Any equation that looks like this, solve it for x2. Well, in this case, it's pretty simple, right? I'm just going to subtract x1 from both sides. So I'm going to have x2 less than or equal to 14 minus x1. Yep, there you go. Okay, so now I have to draw in that constraint. Well, that constraint, right, remember, your equation of a line. This is my y-intercept, and then this would be my slope. So you can imagine there's a 1 in here, right? So 14 is my y-intercept, and I have a slope of -1. So I am just going to have a line, right, a straight line, right, linear, okay, down to here. And of course, this is 14 right there, okay? Now, once again, draw, let's get this color. So, this is less than or equal to this, right? So I'm in that region right there, okay? So what I'm trying to point out is let's see, right? The area here that satisfies all of my constraints, let me do this, is this area. Let me do this. Right, is this area right there. Let me just color this in. Sorry. Okay, there. So, anything below this, right, satisfies all three constraints. So, all this stuff up here, we don't have to worry about. And now, yeah, look at that. Okay, there. See, that's when I've learned something. Look at that. Your professor is learning. Much like you will be. Okay, so at any rate, here is the area in which our objective function can be maximized, right? So how do we find this? Okay, so first I'm going to erase this, whether I'm done with this. Okay. So now right, there we go. So now I got to deal with my objective function. So how do we handle that? Well, what we're going to do is you're going to take your objective function, so 5x1 plus 10x2, and then just say let it equal some number. So I'll call it C. And you can, or profit, whatever you want, right? Just let it equal some number, okay? So this is any level of profit, all right? Now I want to take this equation and solve it for x2. So I'm going to get 10x2 is equal to C minus 5x1, or x2 is equal to C divided by 10 minus 1/2 x1. Okay? So again, this is a straight line or a linear function. x2 is on my vertical axis, x1 obviously is on the horizontal. C divided by 10 is my y-intercept, and then my slope is a -1/2, right? Okay. Well, what's the point of all that? Well, this is the way I would like you to think about this. So see, C is any number we want it to be. So let C equal 10, right? So I'll write that here. What this means, right? That means that your profit, right, 5 times x1 plus 10 times x2 is equal to 10. That means I have a profit level of $10, right? Well, then just plug this in. The reason I'm doing it this way is I'm going to do this in multiples of 10, obviously, because, 10 divided by 10 is 1. So this would be my profit function or my objective function, right? I would have, if c is equal to 10, I would have 1 minus 1/2 x, right? And since I have a slope of a -2, right, I would, if I start here, I would end up here, right? So this, just bear with me, this, okay, I don't know why that did. Stupid marker. There we go. Okay, that was difficult. Ah, darn it, that was really crappy. All right, this gets hard. There we go. Okay, so that is what my profit line or my objective function looks like if I had $10 in profit. Okay. Now the reason that I want you to be thinking about this is because now what we're going to do mentally is let's just keep increasing the profit. So let the profit go to 20. So then I would start at 2 and go to 4. If the profit were 30, I would start at 3 and go to 6. Blah, 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 right? So for example, what if C were equal to 80, right? So then I would have 80 divided by 10. Well, that would put me right here, right? And I would go from 8 down to 16. So I'll draw that one in. Okay. And, here would be 16. Well, what's the point? You can see that I can still go to higher and higher levels of profit, right? And so the idea here is, well, okay, how can we do this? Or how can we do this so we don't have to keep drawing in? These are actually what we call the ISO profit lines. How can we do that so we don't have to keep drawing in all these ISO profit lines? Well, I'm hoping that you can take a look at this and you can say, well, you know what, Dr. Lesh? There look like a few points here that seem like obvious candidates. So let me get a color. Purple. Right, so I'm going to have a kink point right there. And then I'm going to have a kink point right here. Now, right, this is the kink point where this, my first constraint intersects the third constraint. And then, of course, this kink point is where the second constraint intersects the third constraint, right? And the reason I'm saying that is because you can just imagine if we keep moving out our ISO profit line, right, we're going to reach a maximum when we either hit this kink point or that kink point, okay? And that's the idea. This is in your book. So essentially what Excel or any of these other computer programs are doing is they're finding all of these kink points, right? And they're saying, okay, I'm going to find these kink points, and then I'm going to plug them into the objective function. And the kink point that returns the highest level if it's a max problem, or the lowest level if it's a min problem, well, that's my solution, okay? And so that's what we're going to do here. So now, so like in reality, you don't even have to draw these ISO profit lines. I just wanted to draw them in so that you could see as I kept on increasing my profit, right, that I would hit either this kink point or that kink point, and one of these two is going to be where I maximize my profit. So with that said, I'm going to get rid of this, and so now our task is to find those two kink points, okay? Well, here, I'm going to start here. See, I already know that x1 is already 12, right? So I got to get a new color, sorry. I don't want to be writing in purple. I don't mind highlighting in purple, but I can't draw in purple. So I digress. If I go back to this kink point here, I already know that x1 is equal to 12. So all I have to do is plug 12 into my third constraint and solve for x2. So in other words, 12 plus x2 is equal to 14. Now, I know that I've gotten rid of the less than or equal to, and I've replaced that with equal to, but that is okay, because in this case, that's exactly right. I'm saying, you know, when does constraint 1 equal constraint 3? So that's, I just substitute x1 equal to 12. Okay, well, the point is, you can clearly see that x2 is equal to 2. So this point here is the point 12, 2. All right? And now I need to find the point for the other constraints. So we'll get rid of that. And it's the same thing, but now that I know that y2 is equal to 8 at this point, I'm going to substitute 8 into my third constraint and get x1 plus 8 is equal to 14. Therefore, x1 is equal to 6. So this point here is the point 6, 8. All right? And now that I've got both of these kink points, I can plug both of these into my objective function and find out which one yields a higher level of profit. So I'll take the first one. So 5 times x1 of 12 plus 10 times 2, 60, 80, right? That would be 80. 5 times 12 is 60, plus 20 would be 80. And then I'll plug in the other one. So 5 times 6 plus 10 times 8. And obviously I'm going to be well above that, right? 30 plus 80, I get 110. So here we go. There you go. That is the point at which this objective function is maximized. So what this is telling us is that this firm should produce 6 units of good 1 and 8 units of good 2, and by doing so, it will maximize its profit of $110. Okay, and you know, that's how we go about it. So what I wanted to say is, despite the fact that this is all hand drawn, I've actually done a fairly decent job, because what I'm trying to get you to see is, why did this work? Why did these kink points work? Because the slope of the objective function is different from the slopes of all of the constraints. Okay? Now I want you to keep this in mind, because in my 4th video, when I show you what happens when the objective function cannot be optimized, what you're going to see is that the slope of the objective function is actually parallel or the same slope to one of your constraints, right? And so when that happens, for example, if that were to happen here, then anywhere between 0.68 and 12.2, you would maximize your objective function, right? So in that case, we could not find a unique solution, all right? Now that's just a precursor to the 4th video, all right? At any rate, that's it. So that's how we would graphically solve a maximization problem. Again, I want to reiterate, I don't expect you to do this graphically, but I certainly hope this makes sense, because this is what's going on inside the computer. All right? So with that said, we are done, and I will see you in video 3, where we graphically minimize our function.